Hi, welcome to the breadboard. This is part 2 of many parts, I don't know how many yet, of a motion control system tutorial set. In this video we're going to look at the electronics, or start to look at the electronics that are required by a typical motion control system. I'm going to try and keep it fairly generic if I can at this point. Ultimately, in a future video or future videos, we will be, or I will be building two different CNC machines, both being 3D printers, but using different techniques for the motion control. One is going to be Core XY, the other one is going to be a more traditional Delta style printer. We will also be looking in detail at my existing two CNC machines, one of which we've seen in earlier videos, another one which has just been completed except for the final part of wiring up the controllers and things like that. So we will be looking at that in a video as well. But for right now, I just want to go over the basic control systems that is common to any motion control style system. So that would include 3D printing, laser cutters, simple laser printers, CNC routers, plasma cutters. It doesn't really matter. Even a robot arm, technically speaking, would fall into the same category as well. So without further ado, let's get started. Okay, so what we have here is a very high level block diagram of the components required to do any three-dimensional design and fabrication. It doesn't really matter whether it's a CNC router cutting away wood, a 3D printer adding plastic layer by layer, or whether it is a laser cutter cutting holes out of just two-dimensional surfaces. The basic components are all the same. You have to start out with some kind of CAD software. The examples I've got here are either Fusion 360 or DS Mechanical, which is available from RS Components for free. What you do here is you basically design either your two-dimensional or three-dimensional product that you wish to manufacture, and once you're complete you can then export it through a piece of CAM software. So CAD stands for Computer Aided Design, CAM stands for Computer Aided Manufacturer, and often the term CAD-CAM software is used as a single word to define both the design process and the first step of the manufacturing, where we will output machine compatible code, or another term for that would be the toolpaths needed for operating the machine. So things like Fusion 360 and DS Mechanical can both act as a CAD software where you can model your designs, and then they will also, or in most cases, have the ability to output the, in this example, G code required to drive a Gecko compatible CNC controller. Now that could, as I said, be a 3D printer, a laser cutter, or a CNC router if you want. Other software don't take G code directly. For instance, the laser printer that I have actually takes software that you have to use RDWorks to convert into machine compatible instructions, but you can output DXF files from both DS Mechanical and Fusion 360 and others that can be loaded into that software very, very easily to then do the CAM part of the operation. Anyway, I won't dwell into more of that. We will have a look at the CAD-CAM software in a little more detail in separate videos. So assuming that you've done your design and you've outputted in a machine compatible format, it would then normally go to some kind of preprocessor. Now, this could be, in the cases of what I'm showing here, are things like Mark III or Mark IV. This is specifically for CNC work, either CNC router, CNC lathes, plasma cutters, where it takes G codes, provides you a user interface similar to the one I'm showing right here. Also things like Universal G code sender. The Mark III/Mark IV you have to buy. It's not hugely expensive. A couple $100 or so would get you a license for it. the Universal G-Code Sender is free. The two CAD CAM software I mentioned, by the way, DS Mechanical and Fusion 360, depending on your status, is either free. Well, DS Mechanical is free always. You just have to register with RS Components. Fusion 360, if you're still a student or an educator, you can get Fusion 360 for free. If you're not, then you can still get it at a fairly reasonable price. The pre-processing software, what its job is to take the G-code or the AI file, if you've done it from Adobe Illustrator, or a DXF file if it came from or is going to a laser cutter or something, and convert it into basically step and direction instructions for the motors that you have connected to your device that you're controlling that's going to be doing your processing. Now, I say motors without being more specific because the combination of the motor driver and the actual motor, it could be a stepper motor or it could be a servo motor. It really doesn't matter which, and a lot of the servo motor drivers still take step and direction pulses from the controller. It's just how they interact with the motor which is different, and we'll cover that in future videos as well. To get back to what we were referring to a moment ago, the preprocessor will take these G-code instructions. Let's just stick with the G-code, and here's an example right here of what G-code would look like. It basically says things like go to this coordinate, turn on the spindle, lower it into the work surface 5 millimeters, and now form, trace out a path making a circle of a certain diameter, for example. There are instructions like that that are part of the G-code. It can handle a lot of different things, and you just need to tell the preprocessor what the capabilities of your step generator is. In some cases, a step generator can handle the G-code almost natively. For instance, the Mark III motion control card, you can send a lot of the G-code instructions straight to it, and it will actually interpret circles and things like that. But because some machining operations can be very, very large, it will only take parts of it at a time and interpret it, and then get a next piece and the next piece and the next piece, and it will try and optimize the cutting for your work, but basically it just offloads some of the work that the preprocessor could do. Now, in cases like Mark III or Mark IV, if you have something like a parallel port directly connected to it, then on your PC that's running Mark III or Mark IV, then the PC can actually control the step and direction lines directly, thereby making the PC the step generator as well. But you have to have a PC that's capable of doing that, and things like parallel ports are becoming harder and harder to find these days. But either way, there are solutions that, if you're using a laptop, or in my case, I often will use a Microsoft Surface tablet kind of computer, but it has a USB port, then I can run Mark III or the Universal G-code Sender and send it to a separate step generator, which can be either the Mark III motion control card, which is designed specifically for Mark III, of course, or I could use something that's running a G-code interpreter, like a Gerbil for the Arduino, and I'm showing an Arduino here because that's one of the examples that we will be looking at as we go through. Now, neither of these two boards can drive the stepper motors directly. They don't have the capability or the power to do that. What they do is things like convert a circle command into the necessary X and Y step and direction pulses to drive the motor to actually trace out the circle, in this case, that was defined either in plastic or by dragging a cutter through wood or a plasma torch through metal or whatever it might be. Now, these step and directions pulses, they go into motor controller drivers, which could be either a servo driver or a stepper driver. Now, we're going to talk initially about stepper drivers, and mostly because that's what I have. I actually don't have any servo motors at this point in time to show you. And the stepper motor drivers can actually take quite a varied size and price kind of driver, depending on your budget, what you're trying to drive, and things like that. Now, I have 3 drivers shown here. Two of them are Gecko Drives. The first one is a 20X, a Gecko Drive 20X. It's capable of handling up to about 7 amps and can have a supply voltage of about 80 volts. So it can drive motors from very, very tiny stepper motors all the way up to things like NEMA 42s, which are very, very large motors, without any issues. Now, if you're driving the bigger motors, you have to put a heatsink on it. But aside from that, it's quite a capable driver. It's got certain levels of protection built in. It's got opto isolation, which we'll talk about when we talk about connecting up all of the different control systems and things. And I will take you through very specific examples of hooking up the electronics, actually doing the wiring for both the 3D printing machines and also my smaller CNC router table, which we're also going to look at adding a laser to. I have the laser module, so we're going to look at doing both of them. Now, the one below it is a Gecko G540 controller. Now, this is actually 4 stepper controllers all built into a single package, and it's capable of driving up to about 5 amps per motor per winding, and it only handles up to about 50 volts for the supply rail. So not quite as high a torque motors. It can still handle up to NEMA 32s. It just can't handle something like a NEMA 42, NEMA 34s, but not NEMA 42s. But anything else, things like the NEMA 23s, NEMA 17s that are often used on 3D printers and small laser machines, or even NEMA 11s and things, it can handle all of those quite easily. Again, you are limited in how much current you can handle without a heatsink, and I think on this one you have to put a heatsink on the back of it if you're driving more than about 3 amps per channel. And the Gecko 20X is also about 3 amps. If you're over about 3 amps, you have to put a heatsink on as well, or you have to monitor the temperature, and if it is getting too warm, you need to put a heatsink on. Now, the other board I'm showing here, this is actually just a very, very tiny board. It's not even an inch in length, and it basically just plugs into this board. This board here is a rack controller that is often used for 3D printers, and you get 5 of these little boards and just plug them onto these 0.1 inch headers, and it gives you a 5-axis controller. Now, for a 3D printer, this would be an X, a Y, a Z, or a Z for those of you in Europe, and a extruder 1 and extruder 2. This also has the capability of turning fans on and off, controlling the temperature of a heat bed along with the interpreter. So these two work very closely. This board here actually plugs on top of this Arduino Mega 2560. And it's, as I said, it's very, very popular, and I have one of these to show, and we're going to use one when we build the 3D printers up. And lastly, you have your stepper motors. Oh, didn't mention, these little boards here, they can handle up to about 2 amps. So you're certainly not going to be driving NEMA 24s or NEMA 32s or anything like that. It just won't be able to handle it. They're also limited even more in voltage. I think you've got a maximum voltage on these of perhaps 30 or 40 volts. I'll put a link to the data sheets. Actually, let me just have a look right now. Okay, so if we're using an A4988 type of board, which I think this is the one here that's being shown, then you can handle about 35 volts and about 2 amps. If you're running a DRV8825 board instead, which is using a TI chip, you can actually handle up to about 2.5 amps, and the voltage now becomes a maximum of about 45. Now, typically though, with this scenario with these boards, you would not be usually running either more than 12 or 24 volts. And if you are running 24 volts, you invariably have to modify this board, because the Arduino Uno and Arduino Mega underneath it will not handle 24 volts onto its V-in pin, which is the same as the connection as the barrel here. It can only handle up to about 12 or so volts. So you would have to remove a diode off of this board so that it doesn't feed down here, and actually power the controller separately. Now, of course, if you're plugged into a computer, it's going to get power through the USB connection anyway. So the stepper motors here that I'm showing, this one here is actually a NEMA 23 stepper motor. When we do the 3D printer projects, we're going to be using NEMA 17s. I have a number of different ones, and what these are, they are basically motors with 2 windings in them. They actually have a lot more windings that are all paralleled up and are wound around the circumference of the motor, and they're driven by the controller, of course. But to all intents and purposes, from an electrical perspective, there are just 2 windings, and they're at 90 degrees to each other. And by controlling the polarity of the power on each of the windings and the amount of current going through those windings, you can make the rotor spin in a controlled fashion. And what it will do is, because the rotor is magnetic, the core is magnetic, it will try to align itself with the electromagnetic fields that are being set up when you energize the coils. So at the very, very basic set, you would think with 2 coils, then you're going to be able to get it to maybe have 4 positions. But because of the way that the stepper motor is constructed, and I'll put a picture of the inside of one up now, it can actually, in most cases with these, it's common to have 200 steps per revolution. Now I have examples of 200 steps NEMA 24s, NEMA 23s and NEMA 17s. I also have examples of 400 step ones, which gives you about 0.9 degrees per step of rotation, as opposed to 1.8 degrees, which is great because it gives you more accuracy. They're just a little bit more expensive to buy. Now, the last thing that I've got on this diagram, though everything I've talked about so far is all very, very generic. So the last thing I've done is I've identified direction as well as limit switches, because when you turn all of this on, it has no idea where the head that's going to do the work is located right away. You know, it may remember it from the last time, but while it's been powered off, somebody could easily move the head to some other location. So it needs some mechanism for homing. Now, the worst and crudest way of doing this is literally to manually move the head to a certain position on the table in a certain height and press a button on the control panel that says, right, it's now in the 0 position. But you better be very, very careful to make sure you get that right. A better way of doing it is to actually put limit switches on the mechanical side of the platform that this is all running on, and at minimum you would have 3 home switches, one for the X, one for the Y, and one for the Z or Z axis. What you can also do is have a limit switch at the other end of the table, so that if you accidentally have some G-code that tells it to go further than the table is physically capable, then you're not going to be slamming into some kind of mechanical limitation, thereby potentially damaging something and having an expensive repair to do. So limit switches are a very, very important aspect. As well as that, they're also very important for safety and things as well as emergency stops and stuff like that. Emergency stop button, it's not used unless there's an emergency. Now, I want to clarify something right away here. A lot of people think, oh, I've got an emergency stop, I'm just going to use it as a pause button when I'm running my electronics. But you don't want to do that. The emergency stop is when something nasty has really happened. You don't care if the job that you're creating gets ruined. You're hitting that button to kill everything except for the person that might be trapped in the machinery, or or something like that. It's designed as an emergency. So the last thing that matters is the work that you're doing. And you're usually hitting this because you're about to do something that's going to be very, very expensive, and a mistake in cutting or whatever you're doing, or maybe somebody's got trapped in the machine and it's going to cut through their arm or rip their hair out or something like that. So it's very important that in these larger machines where you can get caught, and with these bigger stepper motors, they are very, very powerful, you need to be able to stop it very quickly, and it needs to stop it at the drivers. You don't want to have this thing going all the way back to the Mark III and saying, hey, I got a problem, can you deal with it? Because what if this software has crashed and down here it's still being driven? So what you want is the minimal path, and what I've got here is showing that all of these limit switches and home switches and the emergency stop go to the closest point of the motor driver. So it goes into the step generator, but that is directly internally. It gets fed right through to the enables for all of these motors and will kill that. Another way of doing it with the E-stop button, if you really want to go to town with it, is to actually put the E-stop in a circuit that actually kills the power to the motors themselves. So it will remove the mains power supply to your power supplies, the high voltage power supplies that are supplying the motors, and then everything will stop very, very, very quickly. So it's very important to have these. The limit switches too, not the home switches. The home switches can actually work as a limit switch, but your limit switches also will create effectively an emergency stop situation. Because if you hit a limit switch, it means something has gone very badly wrong, and you're already messing up whatever you're trying to create, because it's gone further than it's supposed to. It's a limit. So if you're trying to cut something that's 1 meter in size and you've only got a 1/2 meter table, you've already ran off the side of the available work, and you're about to drive your machine into a hard stop or off the end of the gantry or something horrible like that, and that's no good at all. So the limit switches will kill the application, and you'll have to re-zero, potentially write off the piece of work you're doing and start again. The home switches, they can often be dual function, and I have them dual function on my machines, but once you've done the actual homing, they become limit switches as well, and they should never be hit during a normal processing of the tool paths, like the G-code or the laser cutting patterns or whatever it may be. So just bear that in mind. And now the final piece we've got here is some local display software. Displays either as a remote pendant that you could hold in your hand, and it can tell you what's going on and also allow you to have a certain level of remote control of the work. Or in the case of a lot of 3D printers, the one I currently have, which is a CEL Robox, does not have any displays or control capability at all, except for one button that allows me to eject the filament. The ones that we're going to build are going to have small 128 by 64 line graphic displays on them with a little knob and everything else, which is fairly typical of RepRap type style printers, and we'll have a look at those when we get to looking at the designs of that in more detail. Anyway, that's all of the basic components of motion control systems. Now, if all you have is a tool that moves a job from location 1 to location 2, you may only have one of these axes. If you have something that is doing, say, pick and place, you would have 3 axes. You'd have an X, a Y, and a Z. You may also have a rotational axis, which would be an A, even on pick and place, because maybe you've got a camera looking at the microchips you're picking up and orientating them before placing them onto a PCB. So this is very typical of all of those different scenarios. Even if this was a robot arm, these could be representing the shoulder, the elbow, the wrist, the fingers, and maybe another axis for the wrist as well, or it could be a gripper or something else. Okay, they're all the same basic components. Now the only thing that really changes in all of this is the scale. All right, up this end it's all the same. You've got some design software, you've got some processing software that controls the machine at a high level, a little bit lower level, and then you're really down into the physical electronics and mechanical aspects of the machine. And the only thing, if I'm driving a great big 10-foot by 10-foot gantry CNC or plasma cutter type of table, then I'll have something like these Gecko 201 or 30X kind of drivers that can handle 7 amps. They can drive these great big huge NEMA 42 or NEMA 34 stepper motors, and I'll have probably 2 motors on the y-axis, a motor on the x and a motor on the z, but they can be very, very big motors indeed. Now, as I move more and more towards a small 3D printer, for example, or even a small laser engraving machine, even more important, or a laser cutter, the head that's being moved around is extremely light. It might only weigh a few ounces. In the case of mine, I don't think I've weighed mine yet, but it's very, very light. It's just a small piece of aluminum containing a mirror and a lens, so it doesn't weigh much at all. But if I take the gantry on my large CNC machine, that gantry along with the cutting head, the spindle and things, weighs about 22 pounds, so that's about 11 kilograms, 10-11 kilograms in weight. That's a lot heavier, and therefore it needs beefier motors to control it. But aside from the actual motor driver and the motor itself, everything else is pretty much identical. The motion control card that I'm using, that I've got here, this Mach 3 motion control card, it can just as easily drive a small 3D printer or a laser cutter as it can a great big 10-foot by 10-foot plasma table or something like that. This small, if you're using a Texas Instruments little 8825 driver here, there's no way it's going to be able to drive a motor that's going to be used on a great big table. But if you're only designing for a 3D printer or a small laser cutter using NEMA 11s or NEMA 17s, it's more than enough, and it will do the job admirably. But I have examples of all three of these that we'll be going through over the next coming weeks as we start building the 3D printers and get the smaller of my two CNCs wired up and tested. So you'll see exactly the difference of the motors and everything else. I do have a couple of other slides here just to quickly show you. If I can just flip through them. So here is an example of what I'm going to or what it could be a typical installation. Now I've eliminated all of the actual mechanical parts except for the motors. So we've got the Mach 3 software that drives, provides a user interface for controlling the machine. You have a Mach 3 motion control card. You have some limit switches. In this case, these are inductive proximity sensors that will detect when one of the axes gets near a limit, and actually in this case it detects a screw that I've mounted on the rails. They're steel screws, so they can easily be detected by these. I have a little interface board here, and we'll talk about that in a separate video, that then allows me to connect into this Gecko driver board that then drives the motors. So this Gecko driver board, all it's responsible for is taking the step and direction pulses and converting them into the phases required to drive these stepper motors. The e-stop goes into the Gecko driver board. Remember I said you want to have the e-stop as close to the motors as possible to kill them quickly and effectively. Well, my e-stop in this case is going straight into the Gecko drive, and it's being relayed after that up into the motion control card, which will then inform via the USB the PC that something weird is going on. But the main thing is that if this went straight to the PC and it tried to tell something down here to stop, that's far too long a loop, and there's far too many pieces of software in between that could go wrong and prevent that from functioning. Our little diagram here just shows how we will be wiring up the Gecko drive. Now ultimately this Gecko drive board that I have is going to have an Arduino, probably an Arduino Uno with a custom interface board on here running the Gecko control software. In the case of what we're going to build up, but this is an example where you can easily wire this up using the Gecko G540 or any other motor controller. The basic thing is you've got the step and direction outputs from here, and they're coming down to here. I will be showing you other diagrams using the Arduino, either a 2560 or an Arduino Uno, actually probably both, that will achieve the same thing but far, far cheaper. This actual Mark III motion control card is probably $200 or $300, whereas if you use an Arduino, then it's far, far cheaper. Now the main difference of buying, let me just flip back a second, go back to the previous page here. The main difference between these small boards and buying things like the Gecko drivers is these Gecko drivers are fully isolated. They have opto-isolator inputs from your controller software, the step generator, to these motor drivers. These have opto-isolated inputs on them. So anything that goes wrong here, you've got 80 odd volts floating around on this side. you've only got, say, 24-volt power supplies and 5-volt logic around here. There's complete opto-isolation between the two of them that gives you several thousand volts of protection. Now, the other things you've got is, even in addition to that, things like this Mark III motion control card, it also has full opto-isolation in the USB link coming in all of these output drivers for step and direction. They have opto-isolator outputs, so you have to provide a appropriate wiring to whatever you're driving with that in mind. And you also have all of the inputs are opto-isolated before they go into the electronics here. So this in itself has full protection. It's talking to another board that has full protection. And so the story goes on. And then the USB interface to the PC is also providing lots of isolated protection. Now that's going to the limit of where you've got big industrial equipment, there's lots of noise around, and you don't want to blow up expensive pieces of equipment, right? These Gecko Drives, this single one is about $150. You shop around, the price may vary, but about $150. This Gecko 540 is about $300 or more on its own. This little board here has no isolation, very little power, and it's very cheap. You can pick them up for about $5 to $10 each. But they don't have the same power capability, right? So if you blow one of these up and your 3D printer stopped working, you just buy another one, you plop it in, or you keep some spares, and away you go. These need the protection because the damage that can be done if they went wrong would be far, far more extensive. Anyway, going back to where we were, so that's like a typical installation. You've got your control software, you've got your interpreter that takes the G code and makes it into step and directions. You've got your step and direction interpreter, which takes the step and the direction pulses and converts them into a rotational magnetic field on the stepper motors that then drives the mechanical aspects of your control system. So anyway, I won't delay any further than that. This is about just over half an hour now. In the next video, we're going to look at wiring up one of the controllers for the small CNC machine, and then I will follow on very quickly with that with an overview of just specifically the electronics we're going to use for one of the 3D or both of the 3D printers. We'll get into mechanical aspects of that as we go along. Now I just want to thank a couple of people here. The RS Components has kindly provided my Gecko drivers for me and a lot of my motors, the e-stops and sensors for me for these projects, so that I can show you how to put all these together and build them. And also another company, SMB Solutions, that has provided some of the aluminum extrusions and also the Mark III motion control card that I'm using here. So just a thanks to both of those companies for helping out with these projects and making these videos possible. I hope you like that. I hope it provides you a lot of information. We will be going into a lot more detail of very specific cases as we go through, and we will be looking next at wiring up a Mark III controller to the G20X drives. Right now I have an Arduino Uno hooked up to these. I will also in the next video be looking at how we wire up the G540, which is slightly different, into an Arduino Uno with a custom controller that I have currently connected on my big CNC machine. So that's what you got to look forward to. So I will see you soon. If you like the video, give me a thumbs up. If you don't, well, you don't have to. That's fine. But I hope you enjoy it, and I hope you'll be following on and having some fun and learning in the process. See you next time. Bye.